for me.
Started.
Okay, so let's see. Well, the main idea behind today's, I'd say, presentation is to, okay, so we have a idea of what a measure is and how to define it, but we don't really have a lot of tools to get these measures. Basically, the idea of today's at least two sections is how we can construct measures, basically a set function that acts in like a measure would, I would say. So the outer measure is the first idea of how we can construct measures, and the way it comes, let's see, it comes from a idea in R2 where we try to get a volume of a figure, right? So in R2, if you want to get a volume of something, you can do this by covering it with a certain sets. So let's say rectangles. And the sum of the area of these rectangles is going to be an approximation. And the outer area basically is doing this process like over and over again to the point where we get like the best refinement. And that's what we call an outer area. It's similar to the Riemann integral of I think it's called upper Darboux sum. Well, this is the basic idea. I have like a small sketch here. So we start like by covering it with some sets, and we try to make these sets like even finer and finer. We know the measures of the rectangles, so we do have like a certain idea of what its measurement is. Well, it's a pretty bad one for this case, but we can make this process like better and better. And taking the infimum over all of these is what Carr theory is all about. So we will see that the outer measure that's defined in the chapter is based around this idea. But of course, instead of rectangles, we just speak of elementary sets. And the elementary sets are what we're going to cover things with. And then once we take the infimum, of course, given that we know the measurement of the elementary sets, this is what's going to give us like a notion of an outer measure. And the main difference of an outer measure from a normal measure is, first of all, well, it's defined on the power set. So we're no longer like restricted to a sigma algebra, even though the power set is a sigma algebra. But we'll notice that it's only subadditive. So the moment we're working with the power set, we can't guarantee that this is going to be additive, at least not on the entire space. And of course, you have to check that it's a monotone set function and that it gives measure 0 for the empty set. Does that make sense?
Yeah, that's good.
Right.
Only
So,
one remark though, because like in the measure, it's additive only for disjoint sets, isn't that right?
yeah. No, this works for any set.
Okay, yeah.
But even if you take disjoint sets, I don't think you can't guarantee that you'll always get sigma additivity.
I see.
So, okay, we instead of course we in abstract spaces there's no rectangles basically in most of the cases. So we need a way to speak about like giving measures to certain things, and this is the idea of elementary sets, which was given in chapter 1, I believe, or in the like section 1.2.
Very quickly.
So
very quickly, I want to mention that what you said about the sigma additivity, that's only for measures. The outer measure is in general not even like finitely additive, right? So I think that's an important thing to know. Like when you restrict to measurable sets, it's sigma additive, but in general, it's not.
Oh, yeah, that's true. I see what you mean. Okay, so as I was saying, we need an idea of to replace basically rectangles or things we know the measurement of. So instead of taking rectangles, we basically take what we call elementary sets, and those sets has to basically satisfy these properties. They have to include phi in it. Some books even include that the whole space has to be in it. although it's not necessary because there's a way for you to always cover any set. If two sets are an elementary set, their intersection has to be an elementary set, and the complement has to be a finite disjoint union of members of E. So once we have a concept of elementary sets, now we speak about how what I said about here, where we take even finer and finer covers, and then we basically take the infimum over them. This is precisely what is stated here. So for any elementary sets and a set function, for example, this could be the area of rectangles in R2. We test, of course, give phi measure 0. We define for any set A this outer measure, where it's the infimum of the sum of measures over every single cover. And that's the idea behind basically the outer measure. This does define an outer measure, but I won't go too much into the proof for it as of right now. Well, of course, there's also a main difference in outer measure for what we call measurable. In the case of measure, of course, everyone knows that if a measure is defined on a sigma algebra, then the measurable sets are precisely those in the sigma algebra. So here, in this case, the outer measurability is tested by this formula, where you take any testing set, let's call it T, and then the measure of the set with T plus the outer measure of the complement with T has to be the measure of T. So in a way, it's like you're saying like it's sort of finitely additive, because if you join these two sets, if you take the union of these two sets, it's going to be precisely T. So once we know now that basically this outer measure is what the measurable sets are, we will talk about a remarkable theorem like in a sec. This is also a useful note that if you define an outer measure using a set function on the elementary sets, then you don't have to test like every single test in the set in the space. You can just do it for the elementary sets, and this of course require proof. It's not trivial, but it's something to keep note of because I haven't found it like mentioned in basically a lot of books. So as I was saying now, okay, cool. We have an outer measure. It's on the power set, but how the hell do we get a measure from this? Well, Kerr theory tells us that first of all, the set of all mu star measurable sets, they give us a sigma algebra. And it's more than that, the restriction of the outer measure to this set is going to be a complete measure, which is quite a strong result, actually. I actually wrote the proof for it, and I was going to go over it, but just to make sure that I have time to cover everything, I'll cover the rest of the lecture, and then if we have time, I'll go back to the proof. Just so we don't go over time. So after this result of Kerr theory, which tells us that the measurable sets form a sigma algebra, and conveniently, this measure is complete, actually. So now how do we exactly use this knowledge in order to get a measure? Or more importantly, if we basically pick any random set function, do we guarantee that this outer measure is going to extend it basically? Is it going to, if we take this measure that's restricted to the sigma mu star measurable sets, is it going to be an extension of the set function? Or are even the elementary sets measurable? Well, one can expect them to be measurable, but that's not always the case. In fact, you can give examples of an outer measure constructed from a set function where the elementary sets are not measurable with respect to the restricted measure, which is the outer measure, basically. So this is the idea of why we need a pre-measure. We need basically the set function that we are going to define the outer measure of. It needs to act like a measure, which we're going to state what we mean by that shortly after. And it needs to be defined on an algebra. Those are really important. Without these assumptions, you cannot guarantee that the outer measure is going to basically give you an extension of this set function. And for example, in the case of the Lebesgue measure, where this set function is going to be the measure of the the length of the interval, while we want the Lebesgue measure to be an extension of that function. And the way we guarantee that is to prove that a certain set function acts like a pre-measure, which is what we will define here. A pre-measure acts like a measure, so it maps the finite sets to 0. And if we take a sequence of disjoint sets, we guarantee that it's countably subadditive. So, and this all, of course, implies that it is finitely subadditive, because you can just take a finite set and then you take everything else to be phi. So you get finite additivity. And now that we have a concept of a pre-measure on sigma algebra, well, now this is an important theorem, because first of all, this tells us that the elementary sets, basically, where this is defined, basically the algebra of sets, not just any set, an algebra of sets, the restriction, the induced outer measure, now gives us an algebra. Now the elementary sets are going to be measurable, and now it is an extension. So the restriction of the outer measure to this algebra is going to be the pre-measure, and that's not always the case. They're not always going to be it's not always going to be a measure, and the sets in A don't always have to be outer measurable with respect to E star. But if it's an algebra and the set function acts like a measure, basically, which is what we say here, it acts like a measure on an algebra, then we can guarantee that it's going to all the sets are going to be measurable. And this is important because once we take the induced outer measure, the induced measure from the outer measure, by restricting it to the algebra of measurable sets, which was stated here. Give me a sec. I think it's just a sec. I think I lost it. Okay, it's here. The restriction of the outer measure to the mu star measurable sets, which is a complete measure, is now going to be an extension of that pre-measure. And this is important because this basically gives us a tool to construct measures, because we can start by a certain set function, and if it acts like a measure and it's defined on an algebra, then all we do is we take the outer measure, which is going to be formed using the set function, just like here. And then the restriction of this outer measure is going to give us a complete measure that extends that set function, which is exactly what we want. And that's how we're going to construct the Lebesgue-Stieltjes measure. So here's the theorem. If U is a pre-measure on the algebra and U star is going to be induced from UO, then the restriction of mu star to the algebra is a measure. I think I didn't write it. Yeah, it is a measure. I forgot to write it here. And the algebra here is going to, every element in the algebra is going to be mu star measurable. I won't go into the proof of the first part, but for the second part, I think we have the time to go over it. So we need to prove that the sets here are measurable. So let me just give me a sec. Read the proof. Okay, so first of all, we start from the very definition of the outer measure, which is the infimum of all, the sum of the measure of every open cover. So by definition then, for every epsilon we take positive, we can find some open cover with the property that the sum of the pre-measure of these sets here is going to be less than the measurement of E plus epsilon. And you can notice that, just like I said above, where we can write every set E as a intersection with U plus intersection with A complement. This is what I mentioned here. Where was it? It was in the idea of measurability, where if you take the union of this set with this set, you're going to get the set T. And we can use this fact here in the proof here. So we start from the definition. And remember, we're trying to prove that A is measurable. So we're trying to prove that at the end of it, that we're going to get the measure of A is going, if we pick a testing set, we need the measure of A intersection some set plus A complement intersection another set to be equal to the measurement of A. And this is what we're trying to prove here. First of all, we separate the sets, and because the mu O, these sets are of course going to be in the algebra, and we already stated that the pre-measure is going to be additive. So we can just separate these functions right here. Now, starting from this property here, which we took here, we have mu star of E, which is our testing set, is going to be greater than the sum of Bj. This is here. And now since we proved that the measure of Bj is in fact the sum of these two sets, we just take the sum of them, which is going to be what we did here. Basically replace each of these, we replaced it with this, and we separated the sum. And now, again, we use the property that the measure is monotone. So every single sum here is going to be bigger than the measure of E intersection A. So now that we have this, if we inserted it here, we're going to get mu star of E plus epsilon is greater than mu star of E intersection A plus mu, let's call it 0. Mu 0 of E intersection A plus mu 0 of E intersection A complement. And this is exactly what we need to prove. We need to prove, if you want to prove a set is measurable, you need to prove this. And that's exactly what we did. But because this is all, of course, I forgot to say about this. The first inequality here, this is less than this. This is always true because it's by the additivity of the measure. So you always need to prove, the only thing you need to prove for measurability is that this set is larger than, this value is larger than these two values, which is a bit important. I think it's mentioned in Fallen somewhere, where it's enough to prove that this is larger than these two. Because the one direction is always going to be true.
But I think you meant larger than or equals.
Yeah, you need to prove this value, the singular one, is larger than these two, because the other direction is always going to be true, because T is a subset of these union. So it's equal to them, actually. So again, let's go back to the proof. And this is what we proved here. Proof that A is mu star measurable. So now that we are done with this, let's speak about another important theorem, which is about extending the pre-measures to the measures. We won't go into the proof just for sake of time, but it is available in Fluent as well. After investigation, I found out actually that the theorem actually has a name. It's called the Hanhan-Kolmogorov theorem. And it's a bit lengthy, but the main idea behind it is that you are taking a measure on an algebra and you're trying to extend it to a measure on a sigma algebra. And that's really important because, well, on a sigma algebra, it's basically, you can basically define a notion of limits and analysis. You can do analysis on it. It's basically a lot better than working on an algebra where it's just closed under finite unions. So again, the theorem is that if we take an algebra and a pre-measure on it, where M is the sigma algebra generated from A, then we have a measure which extends the pre-measure. So here we guarantee that we can extend the pre-measure. And this measure actually is going to be the restriction of the outer measure to the sigma algebra generated by something important. This doesn't have to be the every mu star measurable sets. In fact, the mu star measurable sets could be much bigger than this set. For example, in the case of the what's it called, the Lebesgue integral, I think this set is going to be the Borel sigma algebra, and the Lebesgue measure is actually going to be, can be extended further to the Lebesgue measurable sets. So this is just a sigma algebra generated from A. It doesn't have to be the mu star measurable sets. And if we have another measure that extends this pre-measure, then it's going to be strictly less than it for every set in this algebra. And equality can happen if the measure of E is finite. And moreover, if we assume that the pre-measure is sigma finite, meaning that the space can be covered by sets of finite measure, I think, then it is a unique extension of the pre-measure to which is also going to be the case for the Lebesgue measure. So I found this diagram in Royden, actually. You can find it as well. where this is the process of what will happen. We start from a pre-measure on algebra. We go to the outer measure that we described above, where it's infimum sum of every open cover. Every cover, not open cover, every cover. And then the restriction to the measurable set is going to be the measure. To M, not to the sigma measurable sets. So this is basically, these are basically every tool we need to construct measures. Give me a sec. These are basically every tools we need to construct measures. And from what I saw, you can construct even more than the Lebesgue measure from them. I think one more thing that I need to mention. There is another tool to construct measures, which is, I think it's quite important, but it's not mentioned in full because there's actually a very heavy build up to this theorem. And it's called the Rice-Markov-Kakutani, what's it called? Kakutani representation theorem. It's found in Rudin's book. It's in chapter 2. It basically also gives us another way to construct measures, but the build up to understand the theorem, rather even prove it, which is quite a heavy task, is also quite difficult. But I just wanted to tell people about it.
We're gonna talk about Rice representation later on in the book. We have to. That's one of the important theorems of like the first course. So yeah, don't worry about it. We'll get to it when we get to integrals and whatnot. Yeah.
All right, sounds good. So we'll go back to that theorem. So now that we have the tools, we'll start by constructing basically the Lebesgue-Stahlgeist measure, which is a bit of a general case of the Lebesgue measure. The Lebesgue measure becomes just a special case of this case. Well, we already saw what we need to construct the Lebesgue measure. We need a pre-measure. We can construct it on an algebra. Well, in the Lebesgue-Stahlgeist measure, the algebra is going to be we take half open sets, half closed open sets. So they're going to be open from one place and closed from another. And if we take the finite disjoint union of these sets, we get an algebra. And this is also proved in, I think, in chapter, like the very first section, somewhere here. Here. If E is an elementary family, then the finite disjoint union of E is an algebra. So we guarantee that we get an algebra. The elementary sets are, of course, going to be the half-open intervals. I think it's also safe to say, if you are already in the book, that what we're about to do, you can also do with intervals of this form. It won't make much difference. You just have to do it the opposite way, basically. So we take F. It has to be increasing and right continuous. The reason it has to be right continuous is, if you are asking why we need to be right continuous, it's actually in the proof. You will use right continuity to prove that this function here, which defines for every union of half-open intervals, is the sum of, forgot a bracket here, it's supposed to be closed here.
Excuse me. I'm not really familiar with right continuity. Can you please go into what that is?
Oh, it's basically just instead of, that continuity is basically, it has to be continuous from the right and the left. So if you take the limit if you want to check continuity at A, for example, then you have to take limit as x goes to A plus, and it has to be f of A.
I see.
And from A minus. And if there exist both of them, then you guarantee that it's continuous.
Okay.
And what I said just a moment ago, where instead of right continuous, you can actually do this with left continuity, but you can't work with sets of these forms. You have to work with sets of these forms. It's just like the very same construction. Right continuity just plays a role in the proof as well. So anyway, once we take these half-open intervals and we form an algebra, we just have to prove that this is a pre-measure. Because once we prove that this is a pre-measure, then it's very simple. We just take the extension, restrict ourselves, and we have ourselves the Lebesgue-Stahlgeist measure. Well, it turns out to prove that this is a pre-measure is actually not that straightforward. I think I wrote like the main ideas behind the proof, actually. So again, I wrote that we need to be right continuous. It's more clear in the proof. So first of all, we have to check this function is well defined because, well, the union of the half open, this union here can be written in many different ways, and you just have to check that they're equal. I'll leave the technical detail for the book. And now, just give me a sec. Oh, now, okay, of course. Now we have to check that this acts like a pre-measure, basically. So we need to check sigma additivity. So if we take a sequence of disjoint interval, I'll just speak of general ideas because if I want to go, then we would be done by the end of the meeting with the proof. The first part of the inequality, you can deduce by just partitioning ij properly, which, if I remember correctly, you just have to partition these sets in a way such that the union of any sequence of these you need to take like basically subsequence of this sequence of sets in a way that each subsequence, if you take the union of all the h intervals, you will get an h interval again. I think it's written in the book. But using this technique, which I won't go into as well because I'm still trying to figure it out as well, you can prove the first inequality. The second inequality is also a bit technical, and you need to use right continuity. So you first start by saying what right continuity is, which is that you can find a delta such that f of bj plus delta j minus f of aj less than epsilon 2 epsilon. And by the way, here, the reason we didn't take just epsilon to the minus j, if you go into the proof, right at the end of it, you're going to have a certain summation. Every time you have like, we're doing epsilon arguments, and at the end of it, you're going to take like an infinite summation. Having 2 to the minus j just guarantees that once you take the infinite summation here, you're going to get epsilon. So it's just purely technical.
I quickly want to mention something there. I want you guys to like pour over that part of the proof because this is something you guys will do hundreds of times in your life. This 2 to the negative j thing. So it's very important to know. It's a very important technique to know that you have to scale things by 2 to the negative j for a summation. So yeah.
Yeah, that's true.
I would like to stress that myself. I think that is the single most important trick in this course. You'll abuse it in every single topic.
Exactly.
So yeah.
For sure. So every time you basically have a certain proof where at the end of it you're going to take an infinite summation over epsilons, you need to just factor this by 2 to the minus j. So once you take the infinite summation, you're gonna be left with epsilon. It's also present in the proof as well, and you're going to see it like being repeated multiple times. As for the proof, you're going to use the compactness of a plus beta b, and you're going to use basically the fact that these open covers, that you can take a finite open covering of this compact set. So you can basically, again, you're going to do a certain epsilon argument. I'm going to go into a lot of details because I think it's quite a heavy idea, at least in this proof, which is going to take a while to fully appreciate. It's basically present, I think, in the book here, which is the very first part. One thing I have to note that if you can find this somewhere else, it'll be helpful because usually Volant at least leaves like a lot of very delicate details, which make reading this quite difficult. But it's basically just a technical argument, where because like this open cover covers this whole set, then f of b minus f of a plus delta, which is basically the length of this set, is going to be less than it's like taking the length of the interval from the very end point that's covering it from this side, and then you're going to take a1, which is covering it from this side, and you're going to get, wait, no, it's from inside, and going to get a value less than this one. And once you do this repeatedly, this process, you're going to get a value here. You're going to get the proper less than or equal. So you start from f of b minus f of a plus delta, and then every time you cover this by finite cover, because you're covering it from bn plus delta, it's going to be like on this side, and a1 is going to be like a little bit behind. this value is going to be less than this value, and it becomes just a technical proof. And as you can see here, once you take the infinite summation, you're going to get the epsilon 2 minus j is just going to be an epsilon at the end. Again, I'm still trying to fully grasp the ideas here myself, so sorry if I'm not like super clear on these ideas. Maybe someone else can help us like unravel this proof if you have a very solid understanding of it. I think I'll leave like some questions about this proof as well for the end of this session. But the main idea now, after we go through a bit of a technical proof of this theorem, we just have to use Sahn-Kolmogorov and Carr theory, and we get the Lebesgue-Stieltjes measure. So again, the Carr theorem guarantees that we can move from this pre-measure into a outer measure, and then restricting it to the mu star measurable sets, we have ourselves a measure, which is the Lebesgue-Stieltjes measure associated to f. And as a special case, if you take f of x to be x, then this is going to be exactly the Lebesgue measure that I think most of you have to be familiar with at this point. So one thing to note is that the Borel sigma algebra on R is a subset of Lebesgue measurable sets. And in fact, the Lebesgue measurable set is going to be a completion of the Borel sigma algebra. So the Lebesgue measure is not complete on the Borel sigma algebra, but it is complete on the Lebesgue measurable sets if you use Carr theory. And the set function is just going to be the length of the interval. Because if you take our definition of the set function, you're going to get the measure of any interval AB is going to be f of x, f of b minus f of a, which is just b minus a. So you get the usual length of the interval. And it's also important to note that the Lebesgue measure is unique, which is again guaranteed by Sahn-Kolmogorov, because the Lebesgue measure is sigma finite. I think, yeah, it should be. Is it? Can someone verify if this is sigma finite, which I think it is? Haven't thought of it myself.
So are you trying to say what are you trying to confirm is sigma finite? Just R?
Mm-hmm.
Yeah, I mean, just take a union, countable union of
Yeah,
open
yeah.
intervals, right? Like, n to n plus 1 or whatever, n to n plus 2, right? Those are all finite measure, and the union, a countable union of those over the integers is the whole of the real numbers, right? So it's sigma finite.
Yeah, yeah. I got what you mean. All right. So it is sigma finite. And again, Sahn-Kolmogorov guarantees that if it is sigma finite, then it's going to be unique extension of UO, which is the case for the Lebesgue measure. It is the unique extension of the length of the interval that coincides with it on the set of all intervals. Finally, I'm going to discuss a couple of approximation theorems for the Lebesgue measure. I think Folland states them like slightly differently, but they're the same concept. We're going to prove that if we take any Lebesgue measurable set, which is E, I didn't include it. Yeah, I didn't include it. E is Lebesgue measurable. Then for every epsilon positive, we can find an open set that covers E, and the Lebesgue outer measure of O minus E is going to be less than, what is the outer measure? No, it's the Lebesgue measure. Yeah, I think this is a mistake. This is the Lebesgue measure, not the Lebesgue outer measure. There's a problem here. But the Lebesgue measure of the open set minus E is going to be less than epsilon. And if we take a compact set...
What's happening in that containment of sets in point 1? You say O is a subset of the complement of E is a subset of O. Is there some typo there?
Wait, what? I didn't hear you well.
The containment statement you have about the set O, you say O is a subset of the complement of E, which is a subset of O.
No, this is yeah, I think this makes it confusing. It's a subset of R such that E is a subset of O.
Yes.
Yeah, that's what I meant. Probably should have been more clear about that. And here as well, it's not like R minus K. K is a subset of R such that K is a subset of E. Yeah, that's what I meant. So let's see. Okay, I'm going to go into the proof of the first one, and I'll leave the second one for you guys, just for the sake of time. Give me a sec so I can remember what I did here.
By the way, so while you're reading that up, this property in general, the first one is called outer regularity. So you can be approximated from the outside by open sets. The second one is called inner regularity. So you can be approximated from the inside by compact sets. And together, these are called regularity. And well, this is true for any, like, you know, an inner measure makes sense for any topological space with its Borel measure, right? Or with, sorry, it's Borel sigma algebra, I should say. I guess it's I invite you guys to think about why we defined it exactly this way. So, you know, why not open sets on the inside or compact sets on the outside? That's maybe I'll give it as a problem set problem to think about why we did it specifically this way and not the other way around. Yeah.
All right. Yeah, I'll think about that as well. I've actually wondered about that myself. Let's see. Okay. So, okay, I'm going to mention this again. This is the Lebesgue measure, not the outer measure. This is a mistake in latexing. So, I'm going to go over the proof of one. So, from the very definition of the measure, if we take any epsilon greater than 0, then we're going to find an open cover such that the measure of mu is less than the measure of E plus epsilon, because the measure of E is the infimum of the measure of all such covers, if you remember. So this is from the very construction of the Lebesgue measure. And we're going to distinguish two cases. First, we'll start with the measure of E being finite. And this is, of course, we are done, because now we can, because its measure is finite, then we can say that this is mu of measure of U minus measure of E, and E is a subset of U, so this is just the measure of U minus E. This is not possible if E is infinite. You can just subtract infinite, because it would be infinity minus infinity, which is a problem. So because it is finite, we can just conclude the result from here. Now, if it's infinite, then we just take E to be, we write E in a particularly smart way. We just take E to be E intersection R. So this is the same thing. And R is the union of n plus 1 as n goes over z, right? So again, just a bit of set theory. We write this as union of E intersection n into n plus 1. First of all, note that this measure, this set here, is going to be a subset of this set. So it's going to have Lebesgue measure less than or equal to 1 by multiplicity. And I just call them En here. Now, we just pick epsilon to be an epsilon to be epsilon over 3 dot 2 to the n. The result for this is again technical. You'll notice that this 2 to the n is the one we mentioned above is going to show up again, because once we take the summation at the end, then it's just going to be simplified to epsilon. So now that we have this, we pick an open set On to cover this set En, and we already proved that that we can do this for the case of when it has finite measure. So we can find an epsilon such that U of O minus En is less than epsilon of 3 dot 2 to the n. And if we take O to the B union of all these sets, this is going to be exactly the open set we are trying to look for. So if we measure the Lebesgue set of O minus E, which is going to be the union of On intersection E complement, again, we apply the sigma additivity of the measure. This is just going to be, it's called sigma additivity. I'm not sure what it's called, this property exactly, but the union is going to be less, the measure of the union is going to be less than the measure of sum of the measure of each singular one. So now that we are here, all of these, we know the measure of every single one of these. It's epsilon of 3 dot to the n, and this is going to be less than the measure of, as we read it here. And just technical, here we have n in z. So in order to get n to be, this is supposed to be n, not I, technical show, where it's 2 times the sum of n being in n, and then we take the epsilon over 3. It's for the case of 0. So summing these up, we get that they're less than epsilon, and this is exactly what we're trying to look for.
So there's a little typo here, right? You want it to be epsilon over 3 times 2 to the, I guess, absolute value of n rather than just n. Otherwise, like on negative n, you're shooting up, right? So just want to point that out.
Oh, I see what you mean. Yeah. I'll fix it as well after this. Okay. So here we prove that this property is true. This is stated a bit different in form. I think it's just stated that the measure is going to be here the infimum in this case, and it's going to be the supremum of the covers k here. So it's basically the same theorem. I think it's written here.
So by the way, I want to mention a problem I gave you guys last week, right? I asked you guys what's the other natural sigma algebra on a topological space, right? And one of them is obviously the Borel algebra. I realized that was kind of unfair because we haven't covered measurable functions yet. But so I quickly want to tell you guys what this is, if you guys don't mind. So it's called the bare sigma algebra. And what this is, it's the smallest sigma algebra that makes continuous functions on your topological space from, let's say, x to r into measurable functions. This is the smallest such sigma algebra. And the reason I wanted to mention that right now is that the bare algebra, in my opinion, is actually a very useful thing to use. And this is because, for Borel algebra, so usually what happens is like, you have the Borel sigma algebra and you care about measures on it, but the only measures you actually care about it are these regular measures, right? Because in reality, like you'll see all the theorems are, oh, hey, integrals correspond to regular measures, whatever, right? But so you always have to artificially add this extra condition for regular measure, and that can be annoying. It turns out that bare measures correspond precisely to regular Borel measures, so in a way, bare measures are nicer to use, although maybe this is more hands-on in a way. So yeah, I quickly wanted to mention that. That's another alternative way to think about these.
Excuse me, before we go on much further, can we just like take a few moments to ask questions? Because like I was afraid to interrupt a bit before this, but it seems that he progressed a lot. And I want to ask about something that came up way earlier about like measurable sets, if that's okay.
Yeah, sure.
Okay. So I just wanted to ask about like we talked about measurable sets, but how about non-measurable ones? Like how do those look like? And what does the outer measure like measure for them? Like does that value is just like junk or something? Like I also have another question, but I want to discuss this one first. Like, how do they look exactly? Like, I just want to get an intuition about them.
Well, I think the non-measurable sets, at least in the terms of, for example, Lubeg, they're actually pretty difficult to imagine. They're even more difficult to construct because most of them require the axiom of choice to even know how they look like. So they are pretty, I'd say, weird-looking sets. Like if you think about them, if you look at least a couple of non-Lebesgue measurable sets, you'll notice that the construction simply proves that they exist, and they're pretty hard to imagine or at least grasp. I'm not sure if there's like an example that's like easy to see in your mind.
And how about
their measures?
How about their outer measure?
But it's still gonna give a
like
value.
just
I'm not sure if it's going to be infinity or something, but it's still gonna give a value because it is defined from the power set to 0 infinity, so it's going to give a certain value for it. I'm not sure if it's always going to be infinity or not, but it will still give a value for it.
Doesn't always have to be infinity because the second second thing in the definition of an outer measure. So if we take the example we saw very early on in the introduction section from Fallen, all of those NRs were like subsets of the unit interval. And because this is an outer measure, their outer measure must be less than the outer measure of the unit interval, which is equal to 1. So,
yeah,
anyhow,
that's true.
the other question I wanted to ask is that why does exactly the measurability test like eliminate all of those pathological subsets?
Well, I
Because
think
like you went over it pretty quickly, but like how does it capture all the sets like that we care about and like doesn't leave any pathological example at all?
It's a good question, actually. I'm not sure how exactly it does it, but the best of, I think, option it has is that anyway, this case is telling you that the measure is going to be finitely, anyway, it's a finitely additive measure because, again, the union of these two sets is going to be T. So you're just saying that for every set T you take, you can basically, in a way, approximate it by taking the measure inside E and then outside E and summing them up. But I'm not sure like what the exact intuition for it is. Maybe someone else like have read more about it. I'll do try to dig more into it and give you an answer after the meeting as well.
I think some of it's also probably embedded in the proof. If you maybe look carefully at how we use this property to prove some of like category or like Kolmogorov, right? I think you'll notice that this is important. And maybe that's intuition to have. Maybe you get some intuition from poring over the proof.
That's also true as well. So, is there anything else that was a bit unclear?
Oh yeah. So like I just wanted you to go over the intuition behind or I guess the motivation of the Lebesgue stealthy measure. Like why do we need that exactly?
Well, to be honest,
I guess you
outside
did
the case
mention.
of
I guess you did mention it's like a generalization of the Lebesgue measure, but it's not very helpful in the way of motivation, I would say.
Yeah, well, I think I'm in the same spot as you because I do understand like the importance of the Lebesgue case specifically, and I understand like the generalization, but I haven't seen it like in action yet. I don't know if John or Gomez have saw this in other settings as well.
It comes up a fair bit, both in probability and in analytic number theory. One nice thing about it is, so it's not so interesting if f is like a continuous function or whatever, but the fact that you're only imposing right continuity on it means that f can have jumps in it, like step size jumps. So in a way, it lets you kind of put sums on the like series on the same footing as integrals without switching to using the discrete measure. So a lot of analytic number theory proofs of things like Tauberian theorems involve really clever integration by parts with respect to a Lebesgue, Stieltjes, or even a Riemann version is often so it's just
Excuse me.
just a very flexible tool used in a lot of places. I know it comes up in probability a fair bit too.
You might want to check your mic if you're like moving it or something, because like you cut off the times.
Oh, okay. Yeah, I might have been a bit far from it.
Okay. I see.
Anyway, did you
Cool.
get most of it?
Yeah,
Yeah.
yeah, that's fine.
Thanks.
Thank you.
Sounds good. Let's see.
I might post a problem that uses it later, just to prove that it can be useful.
Sounds good. So, do you have any more questions?
I think that's it for now. I have another question, but I think it's better if we leave it till the end.
All right. Sounds good.
Thank you.
So,
Thank you.
well, I think there's just a couple more properties now, and we could have time to cover Kara theory, actually, Kara theory's proof. So now I'm going to illustrate a couple of the bag measure property without proof. Again, I think at this point I left the proof because I didn't know how much time I'm going to take to cover the rest of it. But basically, the first two you guys have to be familiar with. The third one is not in Fallon's book. So first of all, the Lebesgue measure is translation invariant, which makes sense because in a way, if you move a certain interval or any set, you need to have the same measure for it with respect to Lebesgue, because that's the same way for interval. If you move a certain interval, you're going to have the same length. So you want this to generalize even further. And it's going to be dilation invariant. So if you multiply it by a set by a certain factor, you're going to basically move with your intuition about how this would work for sets for intervals. I'd say that's a good way to think about it. I think at least that's the way I think about it. Okay, so it's like if there's an interval and it behaves a certain way, then I'd want the Lebesgue measure to behave like it. Let's say, and the last one is very interesting because there's a problem I solved in Folland, which is I think problem 33, which is not an easy problem, but I asked someone about it and they told me that the reason this is like a important property because is the Lebesgue measure is non-atomic, because and non-atomic it just means that you can't measure sets such that it has positive measures and any subset of it has measure 0. This is the definition of atoms. So these sets can be measured by the Lebesgue measure, because if the Lebesgue measure can measure these form of sets, then it's not going to give us a very good notion of volume. Basically, it's not going to be able to capture this value of, and you're going to notice like several exercises where you can find, if you take any set Lebesgue measurable, you can find sets inside it that have positive measure and are completely contained in it. And an example of this is in problem 33, where you find a Borel measure that that has positive measure intersection. Let me just go to the problem real quick. So here's the problem where you can find a Borel set that if you intersect it with I, you're going to have positive measure, but it's going to be less than the measure of I. And since this is true on 0, 1, just a bit of scaling, you can make this work on the entire R. So you'll never have to be able to measure atoms. So that's just a cool thing I thought I'd mention. Another thing I want to mention.
Does that go for like any subset of A? So even if we like just take A and take off a single point, and
you're going to get
oh
yeah, so that's the definition of an atom. An atom is a measure that verifies this property, and
so
there are atomic measures.
Oh,
I
so
think. Wait. The counting measure it has to be atomic, but I'm not sure.
So there is something extra here, I believe, for the non-atomic. You'd want to say that the measure of B, so you'd actually, right, like you're not allowed to take B's that have the same measure as A, right? Otherwise, as Dark said, it's a trivial problem. Just remove a single point, right? Yeah. So
wait, can you please repeat that?
So I believe to define non-atomic, you'd have to say that there is. So that means that there is a B that's a subset of A, such that the measure of B is bigger than 0, but is less than A, right? Because you don't want them to be equal, because it's basically as Dark said, right? You can just remove a point and now the problem's trivial, right? So yeah, that's not
yeah.
and that's also what problem 33 is telling, that you can have something that's strictly less than the measure of A, right?
Uh,
Exactly. So yeah, I think one example, for example, is the countermeasure on n. For example, the singletons are all of them are atoms because well, if you remove any set from it, then you don't get nothing. So that's an example of atom. I think. For example, in the Lebesgue measure, that you can't do that because every singletons have measure 0. So this is one way about it.
see,
Um,
I see.
Another
Okay.
thing which, let's see, I think also Dark have asked me about this, which is, so I had to point it out. You don't have to expect that your topological intuition is going to move to measure theory, because as you can see, you can get sets that are nowhere dense, so they're in a topological way, like they're really small, but they can have a positive measure set. So not the counter set, actually, this is a mistake, the fat counter set, which is a general version of it. It's going to be nowhere dense and it's going to have positive measure. Moreover than that, you can have dense
Sorry,
sets
how
which
do
are in terms of
how do you spell it? What cancel? I didn't quite hear.
the counter. I think it's counter set. Yeah. The
Wait,
general
you
one, I
said
think
not
it's
the
called
cancel.
it's called the fat counter set or the
Oh,
general
the fast
counter
cancel
set.
set. Got it.
Also, another pronunciation remark. It's actually pronounced dark hue. Correct.
Oh, yeah, I think.
Yeah.
Okay,
Oh my
I got
god.
it. So let's see.
Okay. Cool.
So, and as well, there is dense sets. So dense in a topological way, they're like pretty big sets, and they can have measure 0, such as the Q, of course. What's also remarkable, which is something that one might think about, well, can we use cardinality to determine if a set is going to have a certain measure? Well, one might say no, because in the terms of Lebesgue measure, at least, you can have the counter set which is uncountable, and it still has a Lebesgue measure 0. So just because a set is uncountable, you can't determine anything about it. So basically, you have to be very delicate and careful with how you treat topological properties and certain cardinality properties in terms of measure theory. It can behave quite differently than how one might expect.
Yes, and I do want to say the Cantor set is a very important example in my opinion. So you guys will probably see 1 or 2 problems based on that in the homework.
Sound good. I was actually going to cover the counter set, but I was a bit worried that I won't have like enough time. But I think we can speak a bit about it. Maybe you guys have already like saw it in a certain topology like course or something. But the counter set, like its idea is not very difficult to understand. You basically start from a set, let's say 0, 1, and you basically cut 1/3 of it from the middle, and you just have like what's left here. So you have 2/3 here. I think it's open. 2/3 here and 1/3 here. So then you do the same thing here. You take 1/3 of the interval, not 1/3 of length, 1/3 of the interval. And then you keep doing this again and again. So here you have 2 certain sets. And again, you keep doing this like forever, and you'll get the
I think
counter
it's
set.
actually closed. Excuse me.
Oh, is it?
Yeah.
I think it's supposed to be closed. Yeah, I think you're right. Yeah, it is closed. So it is closed from these two ends. So, and the importance of the counter set is, again, you can use it to prove many different things. Even these properties that we were speaking about in atomicity and problem 33, you need to use the counter set to do so. And the general version is basically, instead of cutting like 1/3 of the size of it, you just pick a certain size, alpha, and you remove it. So these values are going to be different. And then each time you do this process, you just make alpha become smaller and smaller. And if you do this, then you will get like a similar construction to the counter set. It's going to have the same property. It's going to be compact, nowhere dense, but it's going to have Lebesgue measure. The Lebesgue measure of that set is going to be positive. and this is the general counter set. So you constructed basically a lower dense set, which is, again, as we said, topologically small, but you can prove that it has positive measure. And I'll leave the details to you guys to go through. I think Fon discussed them in a lot of details as well. So there's one thing that I didn't understand, which is I'm not sure what they meant by the set of all x that have base 3 expansion. Well, at least, why is it defined this way, at least? Or is this like important to understand instead of just like what I just mentioned?
I think both ways
It's
are useful.
just another way of formally phrasing you're deleting the middle third each time. When you're cutting out the middle third in the first step, if you think about ternary expansions, every number between 0 and 1 starts with either 0.0, 0.1, or 0.2. By excluding 0.1, you're deleting the middle third.
Oh,
And you're just doing
that
that
makes
with
sense.
each digit.
I see. That makes sense. So do you guys have any more questions, or I think we can cover a bit of Carathéry's proof since we have the time. Okay. Let's see.
I actually have to go, so sorry, but thank you for the talk. It was very enlightening.
All right, sounds good. Thanks for hanging out. Right. Let's see. So I'm going to cover the first part of the Carathéry proof, which is that the set of measurable sets is going to be a sigma algebra, and I'll leave the proof of the completion. The proof of that it's a measure and it's complete is much easier. So the way we do this is going to be through two parts. First of all, we're going to prove that M is a algebra, so it's closed under finite union. And then we're going to use this lemma. Well, it's not proven as a lemma, it's proven as a property, but I thought I'd just leave it as a lemma, using this property to just take limits and get to the case of the sigma algebra. So first of all, one obvious thing is that the sigma algebra is obviously closed under complementation, because if you do the test with E and E complement, then if you take the complement of E, it's going to be the same thing. The complement is symmetric, so it won't affect it. So the problem just becomes with the case of taking that the union of mu star measurable sets is going to be measurable. So first of all, by the way, the proof of lemma is just like it follows from induction. If you write it, it's not very difficult. If you start from any two sets, okay? So this is what we want to prove. We want to prove that this is equal to the measure of E, which is our testing set, okay? So now, if E is measurable, then if we pick this whole set to be the testing set, then we can, wait, it's not E, it's A. A is measurable. Sorry, again, problem. A is measurable. And if we pick this to be the testing set, this is usually like a pretty useful property, which is if you choose your testing set properly, you can do like a bunch of tricks in proving certain stuff. So instead of we take this whole thing to be our testing set, and because A is measurable, then the measure of this set is going to be the measure of the same set intersection A plus this same set. So this is now our testing set E intersection A complement, which is what I just wrote here. This, of course, is going to be E intersection A, and what's left of it is going to be B intersection A complement, which is just this one. You apply De Morgan's. So now do we just substitute what we got here about E intersection A union B? We get this property, which is E intersection A, and then we have this one here. Now, if you'll notice, again, B is measurable. So you just have to imagine that this is your testing set. So this is a testing set, this is a testing set, and because B is a measurable set, then this property here applies. So you'll notice that this trick is used a lot, where the choice of this set T can help you manipulate these expressions, basically, which is just what we did here. We took like this to be the testing set and this to be the testing set, So this is just going to be the measure of E intersection A complement. And we are basically done because we proved that the measure of this set is equal to the measure of E. Here. Just substitute them, and it's going to be the measure of E. Again, here just E is the testing set. It was very simple. So we started from here. We got this to be the measure of E, and this proves that A union B is going to be in M. So we basically got that M is an algebra. Now all is left to prove that it goes under countable union. And one thing to note, which is something like I've mentioned like a couple of times now, this is really important because now if we prove the Carr theory that the algebra we talk about in Carr theory is closed under disjoint union, then it's obviously going to be closed under any union, any sequence of sets. Because in that, if you take any sequence of sets and you want to check that they're measurable, then you can construct a disjoint sets from them and you do the test on these sets. It's going to be the same thing. So you'll notice that it is enough for us to prove that this is true for disjoint sequence of sets. So instead of taking any sequence of sets, we take a sequence of disjoint sets. And this is, of course, going to help us because we can apply various properties like this lemma. I forgot mu here. This is supposed to be mu, by the way. Here, it's mu star of E intersection A. So we take a sequence of set n, and we take Bn to be the union of this An. And B is going to be basically the full set. We start from E as a testing set, and we take mu star to be mu star of E intersection Bn, so intersection this union, and the intersection Bn complement. Here, we just use the lemma here, which you can prove. This is the same thing. Mu star of union of A intersection B is just the same as this one here. So this is how we moved from this expression to this expression. And the other one is left the same. Again, by multiplicity of the measure, we have that this is greater than U star of E intersection B as a whole complement. So I guess this nice expression here, U star of E. Again, it's maybe they're not clear like because I'm like speaking about them, but if you do this like on a piece of paper or anywhere, you'll tag along very easily with me. Here we just use the lemma. I even wrote it here. And finally, once we are here, we just take the limit and we are done. Because once we take the limit, it's very easy. Here we use the multiplicity of the outer measure. Again, for some reason I forgot mu here. This is mu of E intersection AI. And the sum of measure of the sets is greater than the sum of the union of the sets, which is exactly what we did here. Supposed to be covered. And that's it. We proved that mu star of E is equal to mu star of E intersection B plus mu star of E intersection B complement. Sorry about the text mistakes here. And we proved that M is a sigma algebra basically. And the proof that mu is a measure is much less easy, much less complicated. So I just want to highlight this property because the manipulation done in this proof can be quite tricky to get a grasp on basically. But you just need to be able to know how to manipulate the fact that this set can be any set in X in the test here. T can be any set in X. So if you choose T properly, you can make a lot of manipulation that can help you prove this stuff. That's why I want to include the proof of Carr theory here. And I think that's basically it for the presentation. If anyone has any more question about anything or any detail that wasn't clear, I can hear about them now.
Yeah. So obviously this this whole procedure that we've done here is has been presented pretty abstractly. Like it's a bit like and I'm not sure if it's only specific to R. And even like in a more general case like R and but even can we apply this procedure even more like broadly, and how would that be useful if you have an answer?
You mean how we can apply what we did here about measurability?
Yeah, the whole thing about going from a pre-measure to an outer measure and then taking the yeah.
Yeah, of
So-
course. This can be applied to basically any case you can apply this. You can also apply it for the product measure. I believe this is also used in constructing the product measure. And there's even like I saw someone mentioned it. I'm not familiar with it, but someone mentioned that you can also use this to construct the Hausdorff measure, which I think is a measure that works on infinite dimensional spaces as well. But I'm not very familiar with. Just saw it being mentioned. So this can be used in more abstract settings, of course. In theory, as long as the things here are true, then you can basically prove that do this on any kind of spaces. It's not just specific to R or Rn.
Yeah, and in general, I mean, all this is saying is that, to define a measure on a sigma algebra, all you need to do is look at a dense subalgebra. That's basically what it's saying, right? And I mean, that should be useful anytime you want to define a measure on some measure space, any measure space, and you only need to define it on some algebra to define it everywhere, right? So,
Yeah.
just intuitively, this should be useful whenever you want to define a measure by looking at specific sets. Yeah.
But I was like, I was more looking for a concrete example of why you might want to do this.
This process?
Like, aside from R, of course.
Yeah, I think one example which I haven't got into, but I'll try to link. I try to find some resources about it, which is what I just mentioned about the measure called the Hausdorff measure. I think Tao mentioned it, but I didn't go into a lot of details about it. So that would be a case in a more general case, I think.
Cool.
Maybe another quick example of where you use this theorem is in probability. One thing that you want to make sense of is when you're defining Brownian motion or general random processes, you want to make sense of what it means to have a measure on a space of paths, which is hard to do because path spaces are infinite dimensional. Like, how do you make sense of the volume of an infinite dimensional set? And so you can actually use this theorem to construct from finite dimensional subspaces, you can construct a measure on an infinite dimensional space that tells you how likely it is for you to follow, for example, a path that passes through this set, or a path that comes back to the start after a certain amount of time in stochastic processes.
Oh, that's pretty cool. I think I'll
Yeah,
look into this example as well.
really useful theorem for things like that, because it gives you a very, very abstract set of requirements to define measures or to extend measures.
For sure, that makes sense. So I think that's it for my presentation, I'd say. If there's any other questions before I stop streaming, if anyone has. Let's see if I didn't cover anything. Yeah, I think that's it for what I wanted to cover through this presentation. I hope I made a lot of sense.